Well, good morning. Hopefully we have some folks here to ask questions today. If there are folks in the chat, go ahead and please say hello or something like that, so that I know that there are folks around. Um, so what we're looking at, what we were going to look at this week, is going to multiple dimensions in quantum mechanics, and Schrodinger's equation in multiple dimensions is quite a bit more complicated to solve, in fact. And and what happens when you do that is you find out that really a lot of the types of problems that we can solve are ones where Schrodinger's differential equation is a separable equation. And we talked a little bit about that in the lecture notes. And we talked about that a little bit previously as well, this idea of separation. When we looked at the time-dependent Schrodinger equation, we separated it out to make a separate spatial equation and a separate time equation that are independent of one another, and then the solutions were linked together, and it was this sort of separate eigenvalue problem. So that's sort of what we were looking at, except now we're looking at just the spatial Schrodinger equation, the spatial version of the Schrodinger equation, and trying to solve that. And we see that when it works in multiple dimensions, we get, of course, solutions that are connected, but equations that are independent, because the separation process actually linked them. So the basic idea of separation of variables is that I have if I have a function of two variables, like, oops, I'm going to have a brush here, not that. Then if I have a general problem with two variables, then, so psi, which is a function of x and y, then you could say, well, it's equal to some not constant, but some function. I'm going to put a little flare on there to indicate this is a capital X, and then and then that's multiplied times some function of y. And this is an assumption. This does not have to be true, but if the potential allows it, then we can see that it's true. So kind of, it's like you make a guess that this is the way the dependence of the function works, and if the differential equation, along with the potential for the Schrodinger equation, that really depends on the potential. If the potential works out, or the potential has the right form of x and y, then you can see that it'll separate out. It will separate out. And it might not work. It might be that when you perform this process that you can't separate out the x and y dependence and stuff like that. And if that's true, well, then you gotta try some other method of solving it. But it turns out that for the potentials we're talking about here, like the square whale potential for the first one, and then the hydrogen atom potential, where the potential energy is only due to the is just the Coulomb potential, which has to do with separation of the two squared, then, or separation just to the 1 over r, then it also ends up working out. I should note also that something that's a little bit different is, what if, for instance, I had two particles in a one-dimensional box? Two particles in a one-dimensional box, then what you would have is that the wave function of the combined two particles, this is kind of an interesting little sidelight, and I didn't talk about it much in the lecture notes, but it turns out to be true. Let's say I've got a 1D box like this. This is the potential. This is supposed to be infinite, and then x is like, here's x equals 0, and this is, goes on here. So this is the, positive x direction and all that. This is at L, and this, at x equals 0, the potential is infinite, and then at x equals L, it's also infinite. So this is x equals 0. And let's say I have two particles in the box, not just one. Then the wave function of the two particles combined. So there they are. There are two little quanta. Maybe they're living inside the box. What's the wave function going to be? Well, the wave function there would be psi. Would depend on two variables. It would depend on both x1 which is the horizontal position of particle number 1, and it would depend on x2, which is the horizontal position of x2. And then you'd have this wave function of the system of the two particles. Not the individual wave functions, but the wave function of the system of the two. Now you'll notice that, really, what this is you're going to guess that this looks something like this. You might make a guess that the wave function of these two is just the product of two wave functions. Like I said, this is a guess. You hope that this is true. It doesn't have to be true. But if it is true, you'll be able to test it. It'll be equal to psi 1, x1, psi 2, x2. Now you'll notice that the only thing that's different here is this I've called x1 and x2. This is x and y. This is capital X, whereas this one I call psi 1. This is capital Y, which I call psi 2. So, formally speaking, the mathematics of more than one quantum mechanical particle living in the same potential is the same as two dimensions. And the solution should be separable. It should have this same, if this works to solve the problem, then this would also work, then that would also work as a wave function. So superficially they're different, mathematically they're identical, formally they're the same. So if I have 3 particles in the box, it's like having a 3-dimensional box. If I have 4 particles in a 1-dimensional box, it's like treating a 4-dimensional problem. So in other words, solving the multi-dimensional box problem is the same as solving for a 1-dimensional box for many particles being in it. Okay, so hopefully there were. It seems like, again, unfortunately, it looks like we don't have any folks that are in the chat. If you are here, just say hello or something like that. But if folks are not finding these question and answer sessions useful, then I'll just I mean I do some preparation for these things. So if you're not finding them useful, please let me know. It's been pretty silent on the discussion boards. Also, so I haven't had a lot of feedback about how things are going for y'all or anything like that, and I'd really like to have that. So if you could let me know how stuff is going. If this is not a good time, then let me know what's a better time. Oh, hi Maggie. Okay, Maggie is here. Glad to see you. All right. So that helps right there, having somebody present at least, so I know that folks are participating here. So. Glad to have you along, Maggie. So if you have questions, let me know. If this is useful or you want to hear me talk about something else, please just say so that I can we can sort of make it as useful as possible to you. But I'll talk a little bit while I wait for your questions to roll in or your comments to roll in. So that separation problem gives rise to a potential slight complication that you never have to worry about in classical physics. And that problem is, for this one, it's not necessarily so apparent, but for this one, it becomes, we're talking about multiple particles, it does get a little bit different. Okay, so notice that there's the idea of degeneracy here in the multi-dimensional box. Namely, the solution for this is going to be, just to remind you, the solution for this, okay, so going through some more example problems would be the most helpful. I'm certainly willing to do that. I'll talk a little bit about this and then why it's important, and then I'll try to think up some example problems in the one for maybe 1D box. Or could you give me if you could give me a little bit of feedback about what sort of example problem would be useful for this, that because we've got sort of 3 lectures to look at. There was I'm talking right now about the 1-dimensional box the 3-dimensional box, and then we talked about angular momentums for the second lecture, which was the Schrödinger equation in spherical coordinates, and then we talked a little bit about the hydrogen atom in the in the third lecture for the week. So if you could tell me sort of what one you'd like to see, what sort of topic you'd like to see example problems on, I'd sure I'd have to think something up, but we could manage something, I'm sure. So the function x, this wave function of psi of x and y looks something like we've got, there's a constant in front, and then there was the sine of n sub x pi times x, this is supposed to be pi, over L sub x, and then that gets multiplied times the sine of n, I'm going to run out of space here, and pi, and sub y pi y over L sub y. Imagine there's a closed parentheses there. And then we said that the energy, which depends on, so I'll put the 2 n sub x and n sub y. So this is an eigenvalue problem with this, these are the eigenfunctions. These are the particular functions at work. And then the energy was, let's see, how did it go? It went, so there's h bar squared pi squared over 2m, and then you see your question just popped up. I'll have a look. Okay, that's useful. So then I'll get one in once I've got this sort of down, and we'll talk right about that as soon as we get it. Okay. Okay, so this ends up being what things look like for the two-dimensional box. That's the energy solution. Okay, so Maggie says she likes to see 3D box example problems with maybe a little bit of angular momentum. Third PowerPoint is, that's, if you haven't gotten to that yet, no problem. It's still midweek, obviously, so no worries there. Okay, all right, so I'll get to 3D example problem, because this is this is a 2D example problem. 3D is very similar, at least. It's just that you add the third dimension here, and there'd be a third sine function that you multiply by. But once you've expanded from 1 dimension to 2 dimension, going from 2 to 3 isn't terrible, hopefully. The idea here is the idea of degeneracy. The issue that there's two different, so the lowest possible n that you could have for n sub x is 1, and then n sub y is also 1. Okay, now that's unique. Now it would have a particular energy, which would be, whatever L sub x is and L sub y, there's a 1 and a 1 there. So there it is, it's done. Let's say that L sub x and L sub y are the same, so it's like a square box. Then I'll just finish my thought, and then I'll get to a 3D example problem. And then the issue then is, what if, so those are, but notice how when n1 is equal to 1 and n is equal to 2, I get some value here, but I would also get the same value of energy if it was 2 and 1. And that's what we call degeneracy. It's two different, it's the same energy for this first excited state, the next one above the ground state. It's the same energy, but corresponds to two different quantum numbers. One is nx equals 1 and ny is equal to 2, and then the other energy corresponds to nx is equal to 2 and ny is equal to 1. But notice that they have different wave functions associated with them. One, it's nx is equal to 1 and y is equal to 2, and it's different wave functions. So having different wave functions gives you a little bit of a trick in here. And where it's really tricky is in this situation. Because here, what that basically means is that if I switch which particle means x1 and which one means x2, like if I flip-flop those, like 1 turns to 2 and 2 turns to 1, x turns to y turns to x, then that means that these particles are indistinguishable from one another. In other words, it's something we talked about early on. Particles don't have name tags associated with them. I don't know that this is particle 1, this is particle 2. I just know that it's a particle. And this same thing here. So flipping the two should have the same energy, because it shouldn't matter which we label 1 and which we label 2. So And if there's more than one energy, it's called, or there's more than one wave function associated with the same energy, it's called degenerate situation. And you can have many different particles that have the same energy. So, so hopefully that's something that sort of makes sense. So let's clear this out a little bit, give myself a little bit of space to work with. So Maggie's asking for a 3D example problem, maybe something in angular momentum as well. Okay, so example problem time. Let's say I have a situation where would it be okay? Hopefully it's okay if I just do 2D instead of 3D. I would say 3D problems are maybe a little bit more tedious, but they're not any more instructive than a 2D problem because you get the same sort of idea. Let's say that we have a situation where L sub x, so let's say we're doing with a square box, a two-dimensional box problem. Let's say that L sub x is twice as big as L sub y. And let's say that we were asked to find what the first two states were. Let's call them, that L sub x is equal to L and L sub y is equal to half L or something. I want to change that a little bit. I want to change that a little bit. Let's get rid of that idea. Let's say that, let's just change my idea here about what I want to call these things. So let's say that L sub x has a length which is equal to L. It's just, a general L. And then L sub y is twice as big. It's 2 times L, which is twice as big as the x direction. And let's say that the question then is, what are the first 3 energies that are associated with the ground state, the first excited state, and the second excited state. Let's see what those are in terms of L and all that sort of stuff. So I know that the solutions look something like this, and these are the energies. So I'll sort of refix these. So this is E of n sub x and n sub y. It's sort of, those are the subscripts I'm going to use there, and then I've got psi here, which is a function of x and y. Okay, and let's just worry about what the energies are. So I want to know what the first, second, and third excited states are. What are the ground state, first excited state, second excited state energies are for a particle in a two-dimensional box that has these dimensions. So what we'll do is we'll remember what our energies are here, and we can have the situation where we're looking at E 1, 1, and that corresponds to when n is equal, remember, n is all these integers, when E is equal to, or n sub x is equal to 1 and n sub y is equal to 1. All right, so what energy is that going to be? All right, well, it's going to be, all right, so notice that what I can do here is when I look into this expression here, I can see, well, L sub x is equal to L and L sub y is equal to 2L. So what I'm going to do is I'm going to say, well, let's pull that common factor of L squared out here. I'm going to see, well, it's going to be, the energy is going to be h bar squared pi squared over 2m L squared. So there's the common L that got multiplied here. And then I'm going to have, it's going to be nx squared. Okay, we pulled that L out. And then we've got plus ny squared. And then remember we squared Ly squared, so that gives me a 4 here. Okay, so sorry, that's the general energy. This is the, let me erase this here. So that's E of nx and ny. Those are my solutions. Okay, so those are the possible energies that we're going to get. Now, what's the lowest one? The lowest one happens when n is equal to 1. Okay, and when both of the ends are equal to 1. So the lowest energy will be E11. Okay, and what will that be? That will be what, so this, I've got n1, 1 here and 1 here. So it would be 1 squared, which is 1, plus 1 squared over 4. So it would be 1, this factor there would be 5/4. 1 plus 1/4, basically. So I get 5/4, so this would be 5/8, because of the 2 there. 5/8 h bar squared pi squared over m tau squared. Okay, so that's the lowest energy. Now what's the next highest energy? Well, let's think about that for a second. So remember, these got to all be integers. So I could increase n by 1, or I could increase, nx by 1, or I can increase ny by 1. Now let's think about what each one of those does. So if I increase this one by 1, and keep n sub y equal to 1. So this goes, n sub x is equal to 2, and this one is equal, and this n sub y is equal to 1 still. So we're looking at, how does E21 compare to E11? Okay, well, I look at that and I say, well, if that's true, if I take nx to 2, this is going to become 4 plus a fourth. Well, that's a pretty big jump. Okay, so that bracket there, so E21, I mean, this is just a test. E21, we're not sure that this is the next highest energy. We're trying to order the energies. E21 would be, let's call, I just want to save a little bit of writing here. Let's call this factor out here, let's call that E0. Just a common factor right here. That's h bar squared pi squared over 2ml squared. And then this would be, if I'm defining that as E0, that would be 5/4 E0. So E0 is h bar squared pi squared over 2ml squared. Okay, now this would be E21 would be E0 times, well, this would be 2 squared is 4 plus 1, so that'd be 4 plus a fourth. So 4 plus a fourth, that's, let's see, 4 plus a fourth is 16/4, that's 17/4 times E0. That's what will be brackets there. Okay, all right, so that's pretty significant. That's, you've more than tripled the energy by increasing n sub x from 2 to 1, or from 1 to 2. What if we're talking about, all right, so that's true. So what about E1, 2? So keep n sub x 1 and n sub y goes to 2. Well, if n sub y goes to 2, then, all right, so this is still 1 plus 4 over 4. It gives me a factor of 2. 2E0. Oh, well, all right, so that's kind of interesting. So notice I went from 5/4 E0 to 2E0. That's a much smaller shift. So it actually goes E11. It's got to be E12. Okay, so that's a thing. And then, well, what if I went to, what about E13? What does that look like? How does that differ from this one and compared to this one? Well, obviously it's going to go up in energy, but let's check by how much. That's going to be E0 times, well, now what's in our brackets here? Okay, well, it's 1 plus 9/4. So 1 plus 9/4 is 9/4, and 4/4 is 13/4. Which is still less than 17/4. Okay, so now we're seeing what the situation looks like. The ground state energy is actually 5/4 E0. The first excited state is 2E0. And the second excited state is 13/4 times E0. It's not until I get to the third excited state that it looks like E21. Oh, well, actually we should check one more. What about E14? Because we should check that one. That's going to be our E0 times, well, let's check it, see what's in our brackets. All right, so we got 4, so we square that. 4 squared 16 over 4, so it's 1 plus 4, that looks like 5. Okay, which that's 24th, so that's actually, this is bigger. So if I was going to look at the order of these, and maybe I could stretch this down a little bit. If I was going to look at the order of these, I'm going to select this here, so I give myself a little space to work with here. I'm going to get rid of that. If I was going to look at the order, it goes E11, oops. E11 is the lowest energy, then E12, then E13. So there's the second excited state. There's the ground state, first excited state, second excited state. The third excited state would actually be E21. Finally, we get a chance to increase. And then after that, it becomes E14, and so on and so forth. So this would be the order of our energies. Is that useful information? I kind of show you how so you kind of have to check these things to see which order the energy goes in. And the expression there made it kind of obvious that increasing, because ny squared was over 4, that made it seem like, yeah, increasing ny isn't as important for the energy, doesn't increase the energy by as much as increasing n sub x. Does that make sense, Maggie? I'll pause to sort of let you tell me if that was clear, if that was useful. Is there something else that you would sort of like to see, something different? That's a 3D one. That's an example from a multi-dimensional box, at least. So, like a real interpretation. Yeah, there is. It would be. I mean, these really are like particles in a box. I mean, it really does sort of represent if I've got just a cardboard box or something like that with a couple of quanta in it, or one quantum in it. So a three-dimensional box would be an actual box, like a shipping box or something like that. It's just really small. It's got to be quantum mechanically very, very small, and then the quantum lives in it. But it's basically would say the length, the width, and the height of the box are different. And that's true of most boxes. So when we talk about a cubical box, it would actually be that. Imagine a cardboard box where you've got the side length of every dimension is the exact same. It'd just be a cube. So, but what this shows, which is probably a little bit weird, is that the dimensions of the box really, really influence the energies that the particles can have when it's inside there. That's different than what we're sort of used to, because like if you think of a ping pong ball inside of a box or something like that, and then it moves around. Just imagine there's no friction, and there's no gravity or anything like that, and just bounces around inside of the box and scatters and all that sort of stuff. And where it is a matter of momentum and collisions and forces and stuff like that. In quantum mechanics, we say, let's make the box really small, put an electron in it, and it ping-pongs around, bouncing off the walls of the box. Now, where is it going to be? What's its energy going to be like? There certain specific energies that it can have, and that sort of stuff. So, in a sense, that's one way to think about it. Now, what about like a real life example of it? I think some of the examples we did in the 1D box last week sort of give you a sense of how that can sort of be useful. In a 1D box, it's like I've got you could say it's the radial equation of the separation of a pair of quarks in a nucleus, something like that. A proton stuck in a nucleus, which means it's localized in a very, very specific areas. And it's you could do it as a three-dimensional problem as well. You can say it's stuck not just in a one-dimensional space, but in a three-dimensional space, and it's got to be contained within that. Really, probably how you would want to do it is it's a central potential, so you'd want it to do it in spherical coordinates instead of the coordinates we're dealing with here, which are the Cartesian coordinates. So, yeah, I guess that's probably the best explanation I can offer. It's like, think about it just like a cardboard box, and then we'll have to do 3 dimensions, which involves the angular momentum, which is sort of the second half of the question you asked earlier. If you want to deal with it in a more realistic way, like saying, let's put a particle in a nucleus and constrain it to be in a particular space infinitely. Right. Yeah, the box is a box. It can be a box anyway. So hopefully that was helpful. That gives you a little bit of a way to think about how these things work. The other thing to consider also is if the box is symmetric, and the reason why we oftentimes use a symmetric box is because that has a ready interpretation as a one-dimensional box with multiple particles in it. So it's like if I've got a one-dimensional problem with 2 particles in it, and now it's a multi-dimensional quantum mechanical problem, that's interesting. It's something that is realistic. Eventually, next week, we're going to be talking about when we do the hydrogen atom. We started the hydrogen atom now, but of course what we're going to do is all the atoms, not just hydrogen. And to do that, you have to have the complicating part is I'm going to be adding more electrons. So going from hydrogen to helium is going from a 3-dimensional problem with a single particle to going from helium to helium, which is a 3-dimensional problem with 2 electrons in it, and we want to know the wave function of the entire atom involving all of the electrons in it. And then lithium is 3, and beryllium is 4, and boron is 5, and carbon is 6, and on you go, and you got to sort of solve that problem. And they obviously gets complicated. It's many, many dimensions then. But does that answer? Are we good? We can maybe talk about angular momentum now. I'm going to clear everything here, I think. All right. So the angular momentum problem, you'll notice that the mathematics level, once we got we got done with the last exam, the mathematics level sort of went through the roof. Probably you see that the math level here went pretty high. And if I could pull up let's see. Let me look at, I just want to refer quickly to my lecture materials so that I can sort of see what we're looking at here. Okay. Not perfect, but it's okay. Let's see. All right. So the idea is, okay, angular momentum time. Yeah, good time for angular momentum. All right. So angular momentum. So where does angular momentum arise out of? Basically what you do, what you're looking at is you're going to say, well, let's solve the Schrodinger equation. It's that complicated 3-dimensional, in spherical coordinates. Instead of using x, y, and z, we're going to use the spherical coordinates, r and theta and phi. So I'll mention this, just so we're on the same page with regard to what that is. So if I were to draw the axes, the x, y, and z axes, let's say this is the z-axis, and then x is sort of out of the screen, and then y is to the right. Let me check that. Yep, that's right. Okay. So if that's it, then r is just to make sure we're on the same page, like I mentioned. If I look at a particular point here, which is above the xy plane, so here's a vector which points to this spot, and it's going to have, it's going to lie in the xy plane. So what I'm doing is I'm saying this point right here that the arrow is pointing to, it's actually above the xy plane by some amount. So this is sort of what it is I've got, if I were to, put a light down from on high, from the positive z direction, this vector here, which points, I'm trying to make it kind of point out like this. The shadow of it would lie in the xy plane, and there would be some height above the xy plane that point is above. R then is the distance from the origin to that point, so it would be the length of that dashed line that I drew right here. And then this angle right here, measured from the x-axis to the projection that it makes, to the projection downward of it, would be phi. And then I'm just going to extend this out so I can see. And then the angle from the z-axis down to where that is would be the angle theta. So that's this. To make sure that we're using this, know what we're talking about here. Phi is what we call the azimuthal angle. Theta is the polar angle, and r then is the distance from the origin to that spot. Okay, so that's the spherical polar coordinate system. So what we do is we're going to rewrite dx squared plus dy squared plus dz squared, which is the three-dimensional version of second derivatives. We're going to have to write them in terms of d squared r squared and d squared phi squared and d squared theta squared. And it turns out that the Schrodinger, those second order derivatives get complicated quick. There's sine thetas that show up there, all sorts of stuff. So relatively complicated. The thing is that's the solution that you get from that then is a solution which depends that as long as the potential only depends on r, the separation from the origin that the particle has, and this is what the hydrogen atom is. We're putting the nucleus at the origin, and we're saying the electron can be anywhere in here, but the electric potential energy associated with between the electron and the nucleus only depends on how far they're separated. It doesn't depend on where the particle is as long as it's always the same distance away. In other words, the potential has spherical symmetry. And that's why we use spherical coordinates. When you do that, you separate out the variables. You see that every potential that has that property that's spherically symmetric has the same solution. And the solutions are a set of functions, relatively complicated functions, involving Legendre polynomials, kind of like Hermite polynomials, but different, actually a little bit simpler. And e to the I m phi. So you get these two separation constants, L and m. L is the separation constant that comes from theta, and m is the separation constant that comes from phi. And then, so you get these functions, y, l, m, which are functions of theta and phi. And these are called spherical harmonic functions. They have specific, it's an e to the I m phi times a Legendre polynomial in theta. Okay. So that's the solution. And the interesting thing about this is it turns out that L squared, where now capital L that I'm talking about here, now this is not a length, this is actually the angular momentum. The angular momentum can be expressed L times L plus 1 times, this is supposed to be parentheses, there we go, that's a 1 right there, times h bar squared. So, and then when you do the separation and you check the solution out, And you see, because there are limitations on angular momentum wave functions. They have to be single valued. For phi is equal to 30 degrees and 360 plus 30 degrees, you got to have the same value. So there's boundary conditions on these things. Same thing for boundary conditions on theta. Same sort of issues. So what that ends up meaning is L has to be an integer. And so does M. But M, and this has got to be an integer from 0 up to another separation constant, which we'll find out. M has a range of plus minus L separated by integers. So it's integers that run between, that can have values between positive L and negative L. That's it. Now, the interpretation of this, L is interpreted as the overall angular momentum of the system. And M, since it has to do with this azimuthal angle here, is indicating its projection onto the angular momentum's projection onto the z-axis, because it's like, well, how much of the angular momentum is orbiting around the z-axis? So that's why you can have this projection be, have it be as large as L. So the example problems that I've already done, or that I already did there, was noting, well, what are the different values of theta that the angular momentum vector could have with respect to the z-axis for various things. So, and I'm going to say this as well. When you do the separation, there's a third quantum number that leaps out, third separation constant that comes out when you separate out the radial part from the energy. And that's the principal quantum number n. And it turns out that L only works if it's less, solutions only work if L is less than n. Oh, that's not right. It's an integer that's less than n. And n has to be an integer greater than 0. So n is any integer greater than 0. L is any integer that's less than n. And m is any integer that it could be negative between positive L and negative L. Right. Okay. So let's consider then the angle. So this is what happens when you get to the. This is getting a little bit into the hydrogen atom, but this is what you'll end up getting. N has got to be greater than 0. It's the principal. It's any integer that's bigger than 0. L has got to be an integer that's less than n, and m has got to be an integer between positive L and negative L. And then the wave functions of hydrogen would include these times whatever the radial ones are. So let's talk a little bit about the angular momentum then, and hopefully this will maybe clarify some things a little bit. Let's say that I have a state where L is equal to 2. Let's go with L is equal to 3. This will be even better. Okay. L is equal to 3. What's the angular momentum associated with the state angular momentum quantum number L is equal to 3? We call it the orbital quantum number. The orbital angular momentum is equal to 3. All right, so what are the possible values, or what's the value then of capital L, the angular momentum of the state, that's associated with L is equal to 3? Okay, well, it's going to, we could see from this expression down here, L is going to be equal to the square root of L times L plus 1. That's the square root of L, 3, times L plus 1, 4, times, and then there's h bar squared there, so I'll just close that off and say times h bar. So notice angular momentum has units of h bar, just like Bohr was talking about way back in the day. So L is equal to, the angular momentum is the square root of 12 h bar, or 2 square root of 3 times h bar. So that's L. That's what L can be. Okay. And what are the possible values of m then? So m, for every L that I have, m can have a multitude of values corresponding to the possible angles that the angular momentum vector could make with respect to the z-axis. Tells you sort of what theta is. Okay. M is what they call the magnetic quantum number. It tells you the projection of the angular momentum onto the z-axis. So little l was 3. The angular momentum associated with the integer 3 is 2 times the square root of 3 times h bar. M then tells you what the projection is along the z-axis. So it could go, m could be any one of these numbers. It's any integer between -3 and +3. It's all these ones. So the angular momentum, when you've got a state that has a lot of angular momentum in it, relatively lot of angular momentum, with little l is equal to 3, has a magnitude of 2 root 3 times h bar, then that means that L sub z, the z component of the angular momentum, is always equal to m times h bar. Okay, so what are the possible angles that it could have? Well, it could be, or what are the possible values you could have? Well, -3 h bar, -2 h bar, negative h bar, 0, positive h bar, 2 h bar, or positive 3 h bar. Those are the possible values that L sub z could have. So when I was doing the example problem earlier, if I wanted to find out what the angle was for any one of those, that would be the inverse, inverse cosine of L sub z over L. Because when the angular momentum points along this direction here or something like that, it makes an angle theta with respect to z. It's actually telling you what angle theta it makes from the z-axis. And if I look at that, if the z component is this, and then the overall magnitude of the angular momentum is that. So we could find out what all those angles are. We could just say, well, L sub z is, for instance, for when it's -3, it's -3 h bar over 2 root 3 h bar. So if I wanted to find out what that particular angle was, a theta for m is equal to -3. That would be equal to the inverse cosine of this negative z. It might be -3 over h bar over 2 root 3 h bar. The h bars, of course, cancel. You could find out what that angle is, and away you go. So if I would do, I'll just put in here inverse cosine. Oops, calculator needs to be on. Inverse cosine of -3 over 2 root 3. And it gives me 150 degrees with respect to the positive z-axis. So now it's 30 degrees. It's like 30 degrees away from the. It's 150 degrees here. 180 degrees is the pointing exactly down. So there. Does that sort of clarify how that works? Do you have any questions on that? And I'll sort of keep an eye out for the questions, but I'll also sort of discuss this a little bit. So these L and M numbers that come out of that, they pop out of the separation of the two directions, the theta and the phi dependence. L pops out of the theta dependence and M pops out of the phi dependence. And then what we find, like usual, whenever we've been dealing with quantum mechanics with the Schrodinger equation. Okay, good. Glad there are no questions. When that pops, then it's constrained to be an integer because of some boundary condition. In this case, the boundary conditions on the angle. Okay. Do you have anything else that you want to see? Any other examples that you would like to see about how all this stuff works? And while I wait for that to pop up, I will mention sort of my what I want you to get out of Friday's lecture notes, which I know you have probably had a chance to look at that much yet, but the idea is that to give you a sense about where the hydrogen atom, about what the hydrogen atom really looks like, the electron's motion inside of the Coulomb potential, so that we can use that as a foundation for understanding how multidimensional or multi-electron atoms operate. The mathematics is going to be probably, cosmologically challenging. I mean, the solution of those differential equations is pretty challenging. Just to give you a sense of, if you're a physics major, there would be probably a mathematics course taught within the physics major where you would learn the mathematics of all these special functions and stuff called Sturm-Liouville theory and that sort of stuff. And then once you did that, then you would go, then those polynomials and the spherical harmonics and the Legendre and the Hermite polynomials and the Laguerre polynomials, all those sorts of things would be, you would have learned about them already. At this stage, I'm just presenting them to you. The format of the exam is, I'm going to still sort of have the same format as we had before. I'm going to give you more time. So it'll be 4 questions, choose 3. I'll give you basically double time. I'll give you 2 hours on it. I'll open it up after we've, so what'll happen is, the way that it's structured is like, let's say this is just an example. It's not my, don't hold me to this just yet. But as far as schedule goes, we're not sure exactly what the schedule is going to be because we have a couple of sections that we need to do yet. We have to do the other atoms here. But the idea is, let's say that we finish up the material on Wednesday. Let's say we finish up the material on Monday, and we have a question, Q&A or something like that, maybe on Tuesday or something like that, Tuesday or Wednesday. Let's say we do the Q&A on Tuesday to do our review. Then I would say, okay, Wednesday the exam is going to open up. So the exam would open up like on 8 a.m. Wednesday morning, and you'd have till Friday to finish it. But so you could start at any time between Wednesday at 8 a.m. and Friday at 11:59 p.m. Okay, but once you start it, you'd have to complete it in the 2 hours. The way to do it would be the same sort of way you did homework. I expect a little bit more detail with your solutions, but it's just typing in your answers and that's sort of stuff with how you would do it. So I think that's going to be it. So it would be basically the same format, except there would be a quiz, kind of like what your homework is doing right now. So does that answer your question? To be real blunt, I'm not sure that the exam will actually happen during next week. It may be that we'll finish the material and then at the end of the week or over the weekend or something like that. No, you won't have to do that. I'm like, yeah, I just saw your comment here. You're good with that. Like I said, there's going to be a window of time where you could do it. You'll need a 2-hour slot to complete it, but that slot could be any time over the course of 2 or 3 days or something like that. So yeah, I decided I want to be as flexible on that as possible. The other thing is the questions might be a little, I still have to decide on sort of the level of the questions that I want to do, but that's my own problem. It's not something you all have to worry about. Any other questions? How's homework going? It seemed like it was going okay. I graded the homework you turned in last week, it seemed like was all right. I posted them up this morning too. Okay, good. Yeah, the homework is. I mean, part of the point of the homework is to get you a little bit familiar with the mathematics surrounding what's going on. Some of it, like when we did quantum mechanical tunneling last week, some of that was just sort of a plug and chug exercise. But the stuff previous to that with the harmonic oscillator, that took some effort, I'm sure, to get some of those integrals done and stuff like that. But I'm glad it seems doable. The problems in the exam, of course, will be probably a little bit more doable. Yeah, they take a while, so I'm not going to put problems exactly like that, but it'll be stuff where you'll have to interpret some things and show that you can mechanically use some of the expressions and understand what they mean and that sort of stuff. So hopefully that'll be all right. So anything else that you want to ask about? Are we feeling all right? Because we could call it here. We're right about an hour. A little under, but I want to make sure you get any questions you have answered. Especially if you have homework questions or something like that, I can give you a little bit of a push in the right direction. Okay. All right. Thanks, Maggie, for being here. I guess we'll see you next week. Have a good rest of the week. Okay. Goodbye now.